There is currently a great deal of research on the development of novel metal organic frameworks for use as adsorbents in a variety of applications for mixture separations. The objective of this presentation is to consider the methodologies for evaluating MOFs for use in PSA technologies. The MOFs can be compared by using breakthrough experiments on a laboratory scale. Screening and comparison of MOFs can also be carried out by using the Ideal Adsorbed Solution theory for mixture adsorption equilibrium. This theory uses the unary isotherm data as inputs. The modeling of the fixed beds using shockwave approximations provides insights into the metrics that govern the separation performance of MOFs in fixed bed adsorbers. We also consider the use of breakthrough simulations for comparing and evaluating MOFs. The separation of alkyne-alkene mixtures is important in the process industries for preparation of feedstocks to polymerization reactors. The alkyne content in the feed mixtures should be less than about 40 ppm. The separations are usually carried out in fixed bed adsorbers packed with the appropriate MOFs that relies either on van der Waals interactions or selective binding of the alkyne with respect to the alkene. This graph shows breakthrough experiments with two different MOFs, ZUL 100 and UTSA 200. The dimensionless concentrations at the exit of the breakthrough tube are plotted against a parameter that represents a modified time axis. Here the actual time in seconds is multiplied by the volumetric flow rate at the inlet to the breakthrough tube, Q0, expressed say in liters per second, and divided by the mass of adsorbent in the bed, say expressed in grams. This is a convenient parameter to use when comparing MOFs in breakthrough experiments where the mass of adsorbent is not exactly the same, or the flow rate at the inlet is also not exactly the same. So this parameter is a kind of an effective time axis. This graph shows the breakthroughs for mixtures of ethene in a breakthrough tube packed with ZUL 100 or UTSA 200. During the time intervals indicated by the arrows, the desired ethene with a required purity of less than say 40 ppm can be recovered. From these breakthrough experiments, it is also clear that the productivity of pure ethene is higher with ZUL 100 than with UTSA 200. A similar set of experiments for propine mixtures is shown on this graph, where the data are plotted in the on the right hand side using red circles are for NK-MOF 11, and the green squares represent the data for CIF6 2 copper I. The arrows here indicate the relative productivities for purified propene using NK-MOF 11 and CIF6 2 copper I. Clearly, a visual inspection will show that NK-MOF has a higher productivity than CIF6 2 copper I. The use of breakthrough experiments to evaluate and rank a large variety of MOFs for a given separation task is a very time-consuming exercise, and for initial screening purposes, it is preferable to use the IAST for the purposes of preliminary screening and evaluations. The IAST stands for Ideal Adsorbed Solution theory, and this theory was developed by Myers and Prausnitz in a classic 1965 paper published in the American Institute of Chemical Engineers journal. The essential feature of the IAST is the invocation of the Raoul's law for vapor-liquid equilibrium for use to describe mixture adsorption equilibrium. The partial fugacity of component I in the bulk gas mixture is equated with a term which is the sorption pressure of component I times the mole fraction of that component in the adsorbed mixture. The adsorption selectivity is defined as the ratio of the molar component loadings of 1 with respect to the molar loading of component 2 divided by the ratio of the partial fugacities of components 1 and 2. This expression may be rewritten in this form in terms of the mole fractions x1 and x2 of components 1 and 2 in the adsorbed phase. And in view of this relationship, this expression can be rewritten as the ratio of the sorption pressure of component 2 divided by the sorption pressure for component 1. The sorption pressures of 1 and 2 are calculated such that they yield the same values of the spreading pressure pi for pure component 1, pure component 2, and for the mixture. In this integral, these terms here represent the unary isotherm, say the dual Langmuir-Freundlich fit of the unary isotherms, of the pure components. The term here A is the specific area, say square meters per kilogram of the adsorbent. This specific area is not usually known, and therefore it is convenient to define phi as pi multiplied by A divided by RT, where T is the temperature. Since at thermodynamic equilibrium, P10 and P2 superscript 0 yield the same value of phi, it is clear that the ratio of P2 naught and P1 naught, which is the adsorption selectivity, is uniquely determined by the surface potential irrespective of the composition of the bulk gas mixture. Before proceeding with the use of the IAST for the calculation of the various metrics that are used for screening and evaluation purposes, it is important to establish the accuracy and reliability of the IAST. As an example, we show here the unary isotherms for ethyne and ethene in ZUL100. The continuous solid lines are the dual Langmuir-Freundlich fits. The data are for the unary isotherms are obtained using configurational Bayes Monte Carlo simulations of the unary isotherms and also for the mixture. The mixture adsorption equilibrium data are used to determine the selectivity of ethyne to ethene for ZUL 100, shown by the green squares, and ZUL 200, shown by the red circles. The packing of ethyne is more efficient within ZUL 100, and this results in a higher adsorption selectivity by a factor 4 in relation to the selectivity for ZUL 200. The CBMC simulation shown by the symbols are an excellent agreement with the IAST calculations with adsorption selectivity calculated from the corresponding unary isotherm data fits. Having established the accuracy and applicability of the IAST for describing ethyne-ethene mixture adsorption equilibrium in ZUL 100, let us proceed to determine the metrics that describe mixture separations in a fixed bed adsorber. For this purpose, we consider the experimental data for ZUL 100 is shown by the red circles, and the simplest description of breakthrough in a fixed bed adsorber is afforded by the Shockwave model, wherein we assume that the concentration fronts of ethine and ethene traverse the length of the fixed bed in the form of shock waves. Further details of the Shockwave model are available in these two publications. The use of the Shockwave model helps us to determine the metrics that govern the separation performance in a fixed bed adsorber. Let's first start with the molar loading of component 1, Q1, which can be determined from the IAST. This, in the Shockwave model for a fixed bed adsorber, is given by this expression, where Y10 is the mole fraction of component 1 at the inlet, Ct is the total molar concentration of the mixture at the pressure of 100 kilopascal and temperature of 298 Kelvin. Q0 is the flow rate of the gas mixture at the inlet. MADS is the mass of the absorbent. T1 is the breakthrough time. So if Q1 is calculated from the IAST, we can determine T1 from this expression, where the experimental values for Q0 MADS are used, and the T1 that is calculated is shown by the green line here. It is notable that the experimentally observed breakthroughs have a more distended characteristic than predicted by the Shockwave model. We return to this topic in a few minutes. During this time interval, delta T, T1 minus T2, the delta T from the Shockwave model can be calculated from IAST calculations of Q1, Q2 using this expression. The physical significance of delta Q2 is that it represents the amount of C2H4 ethene that is recovered during the time interval delta T. So delta T can be determined from the IAST calculations of delta Q2. We term this term delta Q2 as the separation potential, and it's the relevant metric for screening because it represents the maximum productivity of pure C2H4 that can be realized in a fixed bed adsorber, which the productivity in this time period delta T is represented by the green arrow, whereas in the breakthrough experiments, the actual productivity is lower than this value because of the distended nature of the breakthrough curves observed in the experiment. The departure from the Shockwave model is primarily due to non-idealities in the gas flow within the tube, could be due to axial dispersion characteristics of the tube and or intra-crystalline diffusion limitations. In any case, delta Q2 is the maximum realizable productivity, and this is calculable using the IAST. The adsorption selectivity is related to the delta time, delta T, determined from the Shockwave model by this expression. And from the selectivity expression, we can interrelate delta T, the time interval between the breakthroughs of component 2 and component 1, with the selectivity. Let's take a limiting case where the adsorption selectivity is unity. In other words, the adsorbent is non-selective. Then both components will break through at the same time, and delta T is 0, and that can be easily derived from this expression. So the Shockwave model is useful to ascribe a physical significance to the adsorption selectivity as it relates to breakthroughs in a fixed bed adsorber. The closer the adsorption selectivity is to the value of unity, the shorter will be the distance between the breakthroughs of components 1 and 2. In the other limit of infinite adsorption selectivity, then the delta T is, can be derived as simply Y20 is the mole fraction of component 2 at the inlet times the breakthrough time for component 1. This essentially also means that as the selectivity increases in value, the separation distance between the two breakthroughs also increases, and that improves the productivity of component 2 that is required in purified form. So based on this analysis, we can conclude that besides the adsorption selectivity, an important metric that governs the separation performance for ethene separations is delta Q2, because it represents the maximum in the productivity of ethene that is realizable with a given MOF. To repeat again, delta Q2, Q1, and Q2 and S adsorption are all calculable from the IAST, but these interrelationships with the Shockwave model allows us to focus in on the relevant metrics for a given separation. So if we are aiming for the highest productivity of C2H4, delta Q2 is the metric we should be looking at. For ethine-ethene separations, this graph plots the adsorption selectivity versus separation potential for 1, 2, 3, 4, 5, 6, 7 different MOFs. Interesting to note that UTSA 200 has a selectivity about 2 orders of magnitude higher than the other MOFs, but it does not have the highest separation potential. The highest separation potential, delta Q2, is obtained with the use of ZUL100. In order to confirm this hierarchy of productivities predicted by the IAST, let's return to the experimental data for ZUL100 and UTSA 200 for breakthroughs in a breakthrough tube. Indeed, we notice that the productivity values indicated by the blue arrows for UTSA 200 and the red arrow for ZUL100 are indicative of the fact that ZUL100 has the higher productivity so the hierarchy of delta Q2 values can be used for screening MOFs for this separation. In order to confirm this hierarchy, we proceed to the next step in our methodology by performing transient breakthrough simulations using a much more rigorous model than the Shockwave model described earlier. In the transient breakthrough simulations, we take proper account of the intra-crystalline diffusion, as well as the fact that the concentration fronts in the actual adsorber will not traverse the column in the form of shock waves, but will have a more distended character that reflects the finite selectivity of adsorption with a given MOF. For separation of propine mixtures, this graph plots the IAST calculations of the adsorption selectivity on the y-axis against the separation potential delta Q2 on the x-axis. We note that NK-MOF11 has the highest selectivity and the highest separation potential in comparison to these 4 MOFs as shown here. As confirmation of this hierarchy, experimental data on the breakthroughs for propine-propene mixtures in beds packed with NK-MOF 11 and Cif6-2 copper I are shown here. The productivities of pure propene are indicated by the red and green arrows, and these are indeed a qualitative confirmation of the IAST prediction that NK-MOF 11 has a significantly higher productivity than Cif6-2 copper I. The next step is to undertake breakthrough simulations in a more rigorous manner in order to confirm the hierarchies of productivities predicted by the delta Q2 metric. The salient features of the model for performing transient breakthrough simulations are described in this slide. We consider a bed of length L. Z is the distance along the bed, which is packed with adsorbent, say zeolite, activated carbon, or a metal organic framework with a mass m sub ADS. The bed voidage is epsilon. The gaseous mixture enters at a superficial gas velocity of u. Q sub 0 is the volumetric flow rate at the inlet, say in units of liters per second. And the interstitial gas velocity inside the bed is the superficial gas velocity divided by the bed voidage, which is V. In setting up the model for transient breakthroughs, we assume plug flow of gas, assuming negligible axial or radial dispersion. The gas phase concentrations vary with Z and time t, and at any Z t, the adsorbate loadings Qi, say in units of moles per kilogram, within the crystallites vary along the radius. And each crystallite of MOF or zeolite is surrounded by a gaseous mixture, and at the surface of the crystallite between the gas mixture is in thermodynamic equilibrium with the adsorbent. The mixture adsorption equilibrium is determined in the simulations using the ideal adsorbed solution theory. The molar concentration Ci of each component in the gaseous mixture at time t in position Z is described by this partial differential equation. The term here, Q bar, is the average loading within the crystal determined by integrating over the volume of the crystal. The adsorber bed is normally divided into 100 slices, and further details of the numerical techniques used to solve the set of partial differential equations are provided in this website. Consider the transient uptake of the gaseous component into the crystallites at position Z in the fixed bed adsorber. The transient uptake of each of the components is described by this partial differential equation, where Q sub I represents the molar loading at the radial position R, and Ni is the flux of component I. The flux of each of these components is related to the gradients of the chemical potential by the Maxwell-Stefan diffusion equations. The Maxwell-Stefan diffusion equations recognize two types of diffusibilities. D sub I represents molecule wall interactions, and D sub ij quantify the correlations in molecular jumps for the ij pair in the adsorbed phase. For solving the set of partial differential equations, we may apply two different discretization strategies. The first one is to divide the crystallite into equidistant radial slices. The second strategy is to divide the spherical crystallite into equivolume slices. The equivolume slices strategy is more efficient because the steeper gradients in the molar loadings occur near the surface of the particle, whereas towards the center of the particle, the gradients in the molar loadings are shallower. In our transient breakthrough simulations, we find that typically using 20 to 100 radial slices is sufficient to obtain good accuracy in the numerical calculations. Interested readers who wish to have more details of transient breakthrough simulations may consult the list of references provided here. The experimental data for ethene separations with ZUL 100 and propine separations with NK-MOF 11 are compared with the transient breakthrough simulations using the methodology described in the preceding slides. The IAST is used for predicting the mixture adsorption equilibrium using the unary isotherm data fits as reported in the publications. The transient breakthrough simulations are in reasonably good agreement with the breakthrough experiments and confirm that the breakthrough simulations can be used to evaluate MOFs and rank them according to the desired separation performance. For ethene separations, transient breakthrough simulations were performed for 7 different MOFs as listed here, and from the transient breakthrough simulations, the productivity of pure ethene containing less than 40 ppm of ethine was determined, and these productivity values are plotted in this graph as function of the separation potential. We note that the productivity values determined from transient breakthrough simulations are nearly linearly related to the separation potential delta Q2 calculated on the basis of the IAST for mixture adsorption equilibrium. This graph demonstrates that delta Q2, calculable from IAST, is a good and reliable metric to rank the productivities of MOFs for producing C2H4 of the required purity. The separation of mixtures of ethine, C2H2, also called acetylene, and carbon dioxide is important industrially for production of pure ethine. Typically, the purity requirement is 99% plus. A Psa scheme for using an adsorbent that selectively adsorbs C2H2 is shown here. It consists of pressurization, an adsorption cycle in which rich CO2 is removed at the top, followed by co-current blowdown, and final countercurrent vacuum blowdown to recover the desired high purity product. Any CO2 that is remaining in the void volume and inside the pores will contribute to lower purity of the product. In order to achieve high product purity at high recoveries, it is important to choose an adsorbent material that practically rejects CO2 entirely into the gas phase and does not adsorb CO2 at all. Let us examine the separations performance of 9 different MOFs, all of which are selective to ethine. These graphs show the IAST calculations for mixture adsorption equilibrium. The left graph here plots the CO2 uptake against the ethine uptake at a total pressure of 100 kilopascal and temperature of 298 Kelvin and an equimolar ethine CO2 mixture. It's interesting to note that FJU90 has a CO2 uptake about 2 orders of magnitude higher than these 3 MOFs shown here, ZNU1, CPL1, NH2, and copper impregnated in UiO66. We return in a later slide to the significance of the small uptake of these MOFs for CO2. On the other hand, FJU90 has also a significantly higher uptake of ethine than the other MOFs. Indeed, the ethine uptake of FJU90 is twice that of ZNU1. The right-hand side graph plots the separation potential against the adsorption selectivity. The separation potential is represents the maximum amount of C2H2 that can be recovered in the desorption cycle. based on this metric, FJU90 is the leader of the pack, and based on selectivity, CPL1NH2 is topping the list of MOFs on the hierarchy of the adsorption selectivity. So the message to emerge from the IAST is not all too obvious, because FJU90 has the highest separation potential, but the desired product is only available in the blowdown phase. So we really need to simulate not only the adsorption cycle, but the desorption cycle, in order to be able to properly evaluate the performance of these 9 MOFs. Let us first examine the separations with 2 different MOFs, FJU90 and ZNU1, and let's first consider the adsorption cycle in the Psa scheme. For ZNU1 and FJU90, the transient breakthroughs are shown in this graph, where the dimensionless concentration at the adsorber exit are plotted against the parameter Q0T divided by the mass of adsorbent. The black lines represent the simulations for ZNU1, and the blue lines are the simulations for ZJU90. The blowdown operations will start just before C2H2 starts breaking through into the column exit. And these are indicated by the black and blue arrows respectively. Since C2H2 is the desired product, it is of importance to have an appreciation of what remains within the adsorbed phase up till the point at which the blowdown operations start. For this purpose, we shall examine the animations for the average loadings in the adsorber as a function of the adsorber length. The y-axis plots the component loadings for Z and U1 as a function of the adsorber length, and this animation to be shown plots the component loadings in the adsorbed phase as a function of the adsorber length for FJU90. Let's start with the development of the molar loadings in moles per kilogram for ZNU1. Red is C2H2 and blue is CO2. The corresponding development of the component loadings in FJU90 are shown in the animation below. Red is C2H2, blue is CO2. It is noteworthy that with FJU 90, the adsorbed phase loading is in excess of 5 moles per kilogram for FJU 90, but for ZNU1, the adsorbed phase loading is 2.8, significantly lower. On the other hand, the CO2 loading here is practically nothing, is about 0.2 or so. Whereas for FJU 90, the CO2 loading is about 1.2. At this point, the adsorption cycle is terminated and the blowdown operations will need to start in order to recover the adsorbed C2H2 that is shown here in red. We still have to wait for the for this point to occur when the blowdown operations will start for the black MOF, which is ZNU1. At this time, the adsorption cycle is terminated and the blowdown will start. The important differences in these two MOFs is clear. FJU 90 has a significantly higher CO2 in the adsorbed phase of the order of 1.2 moles per kilogram. It also has a higher amount of C2H2. But when blowdown occurs, both components will be desorbed and will exit the column simultaneously. We employ countercurrent blowdown, which means that the products are removed from this end. So the amount of CO2 is a significant proportion as compared to the amount of C2H2. For ZNU1, the situation is quite different. The CO2 loading at the start of the countercurrent vacuum blowdown is of the order of say 0.03 moles per kilogram, significantly smaller than the value for FJU 90. So when both components are desorbed, the composition of the desorbed gas phase will be in this proportion for ZNU1. Following the simulations of the adsorption cycle, we performed simulations of countercurrent vacuum blowdown for the selective MOFs. the obtained data on product recoveries of C2H2 and CO2 and the purity of the desired product are plotted in this graph. We choose the parameter Q desorption times the time divided by mass of adsorbent as the x-axis in all three cases. Q desorption is the volumetric flow rate of gas exiting the bed, and this is dictated by the draw-off rate used for the vacuum pump. We employ deep vacuum to desorb the products. Let's first have a look at the recovery of the desired C2H2. The cumulative value of C2H2 recovered from the blowdown is expressed as moles of product recovered per kilogram of mass of adsorbent in the bed. The highest product recovery is realized with FJU 90. But the problem is that FJU 90 also recovers a concomitantly large amount of CO2. The amount of CO2 recovered is the lowest with these two MOFs that practically reject CO2 into the gas phase. But these two MOFs do not have productivities of C2H2 that are comparable with that of FJU 90. The purity of the desired product, C2H2, is plotted against the effective time, and we note the highest purities of about 97% are realized by the MOFs that practically reject CO2 into the gas phase. Whereas the product recovery with the FJU 90, for example, is only 80%, far lower than the desired high purity requirements of industry. A good compromise would be to use ZNU1 that has a high purity of C2H2 along with a reasonably high product recovery of C2H2. In this graph, we plot the C2H2 recovery from blowdown operations against the separation potential determined from the IAST calculations. For all the MOFs, there is a roughly linear relationship between the product recovery from vacuum blowdown and the separation potential, indicating that these IAST calculations provide a reasonably good measure of product recoveries. Let's examine the product purities that are realized after vacuum blowdown. These are the values from the vacuum blowdown simulations shown in the previous slide. They vary from 75% purity for TIF62 nickel I to about 97% for these three MOFs. The product purities are plotted against the IAST calculations of Q1, which is the component uptake of ethyne divided by the total uptake and multiplied by 100. So you can see that there is a practically linear relationship between the IAST calculations of the product purity that is expected in vacuum blowdown with the actual purities that are realized in the blowdown simulations. To stress the point that was also made in the earlier slide, FJU90 has the highest C2H2 recovery, but the product purity is only 80%. Of these three MOFs, ZNU1 has the highest value of the C2H2 recovery, and therefore it is likely that ZNU1 is the optimal MOF for this separation. A different approach would be to select a MOF that is selective to CO2 such that C2H2 can be recovered in the adsorption cycle. This is what we are going to examine in the next slide. Professor Dam Zhao at the National University of Singapore and his group have reported results for cerium 4 mil 144F MOF that is CO2 selective, and this MOF is of potential use for producing high purity C2H2 from a CO2 C2H2 mixture. We present simulations of transient breakthroughs in a fixed bed packed with the cerium MOF. Two types of simulations are compared, one in which diffusional resistances are duly accounted for, and the other type of simulation in which the diffusional effects are ignored, and we assume that the diffusivity is divided by the square of the radius of the crystallite is very large, leading to practical equilibrium between a gas mixture and the particle of adsorbent at any position in the fixed bed. Let's have a look at the two simulations. I will run these simultaneously. I would like you to note that the simulations with diffusion have a more distended characteristic than the simulations that ignore diffusion. If diffusion effects are ignored, you get very sharp fronts. This is the front of C2H2 as it traverses the fixed bed and exits the column, and CO2 that is more strongly adsorbed is leaving the column at a much later stage, leading to good separation. This graph shows a comparison of the experimental breakthroughs for C2H2 and CO2, shown in red and green, with the two types of simulations that were described in the previous slide. The simulations indicated in black are the ones that include diffusional limitations, and the simulations that are indicated in blue are the ones where diffusional influences are ignored. We see sharper breakthroughs with the equilibrium based simulations shown in blue. Sharper breakthroughs result in higher productivities. So diffusional influences have a tendency to lead to distended breakthroughs and lower productivities. The message we draw from this comparison is that for a realistic prediction of productivities of desired products in transient breakthroughs and fixed bed adsorbers, we need to consider intra-crystalline diffusion limitations. The industrially important separation of alkene-alkane mixtures is currently carried out in distillation columns. Let's consider, for example, the separation of ethene from ethane. The boiling points are relatively close to each other, and the relative volatility alpha is about 1.2. For separation of propene from propane, we see that the boiling point differences are about 5 degree Kelvin, and the relative volatility is only 1.14. Currently, industry requires ethene feedstocks to the polymerization reactor to be of 99.5% plus purity. And similarly, the propene fed to a polymerization reactor should also have a high purity of the unsaturated alkene. This is a picture of a distillation column. Typically, the distillation column for separation of propene from propane, this is called in industry as the C3 splitter. Such distillation columns are amongst the largest distillation towers on this planet. They operate at reflux ratios of about 15, contain about 100 plus distillation trays, and in view of the large capacity of such units, the column diameters can range up to 20 meters, and the column heights are about 75 meters. Just to put this in perspective, this is a picture of a human being, and you should consider the height of this human being in relation to the diameter of the distillation column. In view of the fact that these distillation columns operate at cryogenic temperatures, at high reflux ratios and high pressures, they are energy intensive because of the costs associated with vaporization and cooling in the reboiler and condenser operations. So in MOF developments, this separation has been the target for the development of a suitable MOF as a replacement for the current distillation technology. One candidate MOF for use as adsorbent in alkene-alkane separations is MOF 74, where the N represents the unsaturated metal atoms such as magnesium, iron, cobalt, nickel, or manganese, and these are indicated by the blue spheres in this structural representation. MOF 74 consists of hexagonal channels of 11 angstrom size. The M atoms selectively bind with ethene and propene, and the attachment of the alkene molecules is side-on, as shown on this diagram. For alkene selective adsorbents such as MOF 74, here is a Psa scheme that is applicable for propane separations. The scheme is described in the paper by Khaligi. It consists of 5 steps. The first step is a pressurization step, followed by a high pressure adsorption cycle in which purified propane is removed from the top. This is followed by a co-current high pressure purge where any remaining propane is purged using a part of the desired product, propene. The co-current high pressure purge is followed by co-current blowdown, and the gases here are compressed and fed back into the adsorption cycle. And finally, the 5th stage is countercurrent vacuum blowdown, wherein the exit gas contains the desired propene product. Now, the purity of the propene product in the gases exiting the countercurrent vacuum blowdown phase is dictated by the amount of propane that is still present in the void volume and inside the pores. This graph presents experimental data on breakthroughs for propane mixtures using 3 different MOFs. Iron MOF 74 binds the propene selectively, but there is also a significant uptake of propane within the pores, and this significant proportion of propane that is adsorbed in the pores could result in a lower purity in the propene product that is recovered in the vacuum blowdown phase. The situation with these 2 MOFs is quite different. CAUST 7, for example, excludes propane almost totally from the pores by a trapdoor mechanism. The exclusion of propane from the pores has the effect that the propane that is present in the void spaces and within the pores during a vacuum blowdown operation is insignificantly small, and this results in a higher purity of the desired propene product. However, the propene uptake with these two MOFs is significantly lower by about a factor 8 than with iron MOF 74. So the objective in MOF development could be to devise a MOF that excludes propane but has a significant uptake, in any case higher uptake than Caust 7 and cobalt gallate for the unsaturated alkene. Alternatively, we could aim to develop a MOF that selectively adsorbs the propane. The situation with regard to separation of ethene-ethane mixtures is precisely analogous. The use of iron MOF 74 results in the breakthrough shown here with the red circles. A significant proportion of ethane is also adsorbed along with ethene, and the significant adsorption of ethane has the effect of causing a lower purity ethene product in the vacuum blowdown phase. UTSA 280 excludes ethane from the pores because of subtle differences in molecular sizes between ethene and ethane. Ethene is a flat molecule that snugly fits within the pores, and ethane is not flat and gets rejected because the pores cannot accommodate ethane. This size exclusion of ethane from the pores is reflected in the breakthroughs, where ethane breaks through almost near the start of the breakthrough experiments. So this early breakthrough of ethane is desirable in a Psa scheme because it implies that a negligible proportion of ethane will be present within the void spaces and in the adsorb phase during vacuum blowdown operations. There is ongoing research for development of MOFs that selectively adsorb the ethane rather than the ethene. But the obtained selectivities are rather low, as evidenced in the published literature on this topic. This area of alkene-alkane mixture separations is a fertile ground for further research to develop MOFs that can eventually compete with current distillation technology.